Hi everyone, my name is Virag Varga and I'm here to present on behalf of my co-authors Gergely Vakuja, Benjamin Burgisser, Nathan Riopel, Fabio Zünd, Robert Sumner, Thomas Gross and Alanson Sample. Our work is called a real-time capture of holistic tangible interactions. This work is done in collaboration between ETH Zurich, Disney Research Studios and University of Michigan. When we plan to blend the physical and virtual worlds, we often focus on how to get the display right. For example, on how to identify object markers or a horizontal surface so that we can realistically render a virtual overlay. While this experience can be already entertaining and engaging, these applications often focus on a very narrow view of the world and miss the details of the rest of the user's physical environment and her interactions in that environment, such as touching various objects or being present at a certain location. This overall interaction capture problem can easily become even more complex once there is occlusion or when there are similarly looking objects present. In our work, we wanted to find a capture solution for holistic tangible interactions, which could single-handedly cover all the scenarios from the previous slide. Ultimately, we wanted to find a capturing technique which could tell us who is doing exactly what and where, so that we could incorporate these events into the storytelling of the application for a better and more immersive experience. The ultimate question is, of course, what technology would be best suited for such a holistic capture. While there exist various options with different advantages and disadvantages, our proposal is to utilize body channel communication. BCC uses an electric signal confined to the user's body to transmit digital data along the skin. In the tangible interaction capture scenario, this would mean that tangibles could invisibly broadcast their IDs to anyone in direct contact with them. The tangible ID system we propose here looks like the following. In the augmented reality setup, the application starts as normal. The AR camera scans for markers and upon finding them, an overlay is displayed. The difference comes once we start interacting with the objects. We know immediately if the user picks up something and we also know exactly which object that is. Once both are in hand, we can trigger for a special event. The tangible ID ecosystem consists of the following elements. An instrumented object, which can be anything like a book or a bottle or even a lantern. And then of course we have the instrumented user himself. Once the user comes into contact with any of these objects, the touch event is recognized. By the way, it's not just various objects the system supports. Locations can have their unique identifier as well, and even other users. The tangible ID system would support any interaction between these types. Once we extend the system with a display, the event is then forwarded through a bridging mechanism to the application level. And last but not least, in our system, we added an optional developer extension, an Overwatch application which can oversee any network activity from a computer. Body channel communication had been around for a while. Our group published the TouchCom system some years back. However, the purpose of such system was to optimize for generic data stream, making sure that longer messages also arrive intact between the transmitters and the receivers. In Tangible ID, however, the network's purpose is different. Here we want to send short messages to indicate an ID that's picked up through touch. Several questions arise. What should be the packet format? What does error correction even mean? And how should it be applied? What beaconing pace can we use? And what does it mean with regard to touch recognition performance? And last, how can we optimize the system for simultaneous touches? Overall, while building Tangible ID, we had to address several questions. First, as just mentioned, the network protocol had to be tailored to touch recognition. This meant optimizing for reduced latency, even while keeping the identification accuracy high. Moreover, the data forwarding had to be addressed. A hardware iteration was needed to reduce the physical size so that we can integrate the transceivers into various everyday objects. And last, a headset and a tablet integration needed to be considered as well. But we don't have time to go into the details of all these points. Quickly, I want to show some data on how we evaluated the performance. Here I'm going to discuss specifically the simultaneous touches scenario. This plot shows 4 different beaconing strategies that we evaluated, each with different transmission frequency. We had 2 transmitter objects continuously beaconing their IDs, while the user's wristband was set to receiving mode. We can see on the plot that having a slower transmission rate, this can be seen on the left-hand side with 15 to 50 millisecond wait time between beacons. This resulted in more correctly received messages. This case yielded 75% correct transmission, while with the short wait time between the beacons, this performance drops to 43 to 44%. However, when we translate this network performance to a touch recognition metric, then we see that using a 1-second evaluation window, we are actually guaranteed to receive more messages with the more lossy transmission protocol. The higher number of messages are advantageous because then we can be more certain that the touch event actually occurred during the evaluation window as a sort of error correction. If now we want to lower the latency, then we can also take a look what result we would get using a different evaluation window. In this case, we can see that even if the touches are evaluated every 50 milliseconds, we would still roughly get 2 separate ID messages per transmitter. This should be sufficient for accurate, immediate touch detection. Once we build tangible ID, the next question is, what interaction modalities does it enable? We identified the following ones. As a base case, we can achieve context awareness by being able to recognize objects the user is dealing with. This can be extended to a group of dealing with so-called smart objects, either by saving state information or interaction history directly to the object, or by the object understanding the presence of other objects. Next, we can have interactions anchored to certain locations, either by the presence of a given user or by a given object at a certain location. Last, we can also recognize multi-user interactions, such as several users interacting with the same object or the users interacting with each other, like a handshake or a high five. To demonstrate the potential of tangible ID and these interactions, we created a complete showcase set in the haunted castle. Here I'm going to show only a few examples, but please look at the paper or the short video demonstration for the rest of the scenes. In this first example, a ghost is floating around and 2 physical objects are lying on a desk, a lantern and a book. The objects are identified instantly as the user touches them. Depending on which object the user picks up, it kills or summons back the ghost. This example shows how context awareness can be achieved through tangible ID. Events can be anchored to certain locations. Here the player sees a painting of a lady. If the user brings either the lantern or the ghost book close to the painting, and only then, the painting suddenly comes to life. The floor tile in front of the painting can recognize the objects brought there, so the displayed AR content can automatically adapt, even if the interaction is not in the line of sight of the AR camera. In this last example, we show how we can support novel interactions where several users play together. Users can unlock the floor plan and all extra information about it by interacting with a map. If the user tries to unlock the map content alone, they will only see part of it. All users are needed to be present to see the full map. The map is a touch-sensitive object that listens to incoming user IDs. In conclusion, in our work, we introduced Tangible ID, a holistic, tangible interaction capture system. We showed how a generic application workflow should look like, what software components need to be taken care of, and how BCC can be redesigned for such touch recognition. And finally, we identified 7 different interaction modalities, which were then demonstrated through a complete showcase. We hope Our work can inspire future application developers and designers to integrate more tangible interactions for a truly immersive experience. Thank you for watching, and we are happy to address any questions.